In this video, we're going to take a look at how to use Excel to perform a two-sample hypothesis test with either means or proportions. And I'm going to assume, as I move forward through this, that you have in fact watched the last video for one sample hypothesis testing, and that you've watched the video before that on confidence intervals for two samples. The reason I'm going to assume that is so that I don't have to make a 1-hour video, I'm sure you will appreciate, so that I don't have to explain all of the intricacies, but just talk about how things are the same or different from things that we've already learned. Before we talk about this first example together and the scenario that we're going to work through together, I want to just talk about the formulas. So this is sort of putting together things that we've already talked about. We are going to find a z-score just like we did last week for one sample, but our z-score is going to be found by taking the difference of the two means minus the hypothesized mean. So remember, these actually should be x bars. X bar 1 minus x bar 2 minus the expected mean. And typically the expected mean is going to be 0. So we're going to assume that there's not going to be a difference and then find if there is a statistically significant difference. And then, of course, we're going to find the divided by the standard deviation. And the standard deviation for means with sigma known is just like we did before. We're going to find the variance of the first divided by n1 and the variance of the second divided by n2, and then take the square root of that to turn it back into a standard deviation. So as you can see in my z-score formula, I've said, okay, take b1 minus b4, that's the first mean minus the second mean, and then subtract the hypothesized difference, or mu. Typically, like I said, this value is going to be 0. And then the standard deviation is the square root of b2 squared divided by b3, so the first standard deviation divided by n plus the second standard deviation divided by n, and of course the square root of that sum. And then for your p-values, these are all p-values because that's how we make our decisions. Again, left-tailed is norm dist for the z-score, right-tailed is 1 minus norm dist, and then two-tailed is that crazy if-then formula, which again, I don't care if you do it that way, or if you just find the one that's less than a half and take it times 2, because that's essentially what it comes down to, is we're taking whatever the z-score is. If it's a positive z-score, I'm going to the right and taking that value times 2. And if it's a negative z-score, then I'm going to the left and taking it times 2. So let's see how this looks. We have a university researcher interested in a new instructional method for English for a university freshman whose scores require them to complete remedial work. He's comparing traditional two-semester instruction against the new one-semester co-requisite instruction. He wants to test the claim that students who are in the traditional English remediation score lower. So you got to be super, super detail oriented on these questions, because what we're trying to do is determine, again, this is a hypothesis test, so I have to determine my null and my alternative hypothesis. Now, when we did this for one sample, we looked at mu being equal to something and then mu being greater than or less than or equal to something. Now in this case, we're actually looking at mu1 being equal to mu2, and the alternative is that one of them is greater or less than the other. So in this case, because we're saying he wants to test the claim that the students who are in the traditional English remediation score lower, and traditional is our first sample, I'm going to make that a less than. And again, that's going to be super important for which one of these am I choosing, left-tailed, right-tailed, or two-tailed. So this is considered a left-tailed test. Now, I want to point out that you might also see this written as M1 minus M2 is less than 0. Those mean the same thing. It's the exact same thing, it's just written in a little bit different way by moving the M2 to the left side and with nothing left on the right side. So let's go ahead and take a look now at which one is first. So we already said that M1 is going to be the traditional English remediation. So that's my first sample, my traditional course. And then we have other students who are in the new group with the co-requisite. So mean one is 93 randomly selected students were chosen for the study. Of this group, 41 students were chosen to take traditional. So 41 were taking the traditional course. And the group scored a mean of 66.47 with a standard deviation not given yet. The other 52 students, so that's the other group, scored a mean of 69.43. And assume the population standard deviation for students in the traditional English class is known to be 8.05. And for the new class is 9.22. And alpha, or the level of significance, is 0.1. Now let's take a look at what this means. Again, we have found the z-score using this formula. Just like we did last week when we were finding the p-value, that's exactly what I'm doing again. I've got 0 in the middle. The z-score, in this case, remember I'm using a left-tailed test. So I have found that z is negative 1.65. I need to find this area, and then I need to determine if p is less than alpha. Well, p for a left-tailed test is, again, using the same formula we've been using, norm dist. The area to the left is 0.049. Alpha is 0.1. That's given in the question. So is this true? Yes, it is. What does that mean? That means I need to reject the null hypothesis. So again, one of the hardest things is to be able to interpret your conclusion. I am going to reject the null hypothesis, and that means there is significant evidence that the alternative hypothesis is true. What is the alternative hypothesis? Oops, that this is true, which means M1 is less than M2. That means that the mean final exam score for students who took the 2-semester remediation English class is less than the mean score of students in the single semester co-requisite English class. So when we're dealing with 2 samples, again, we're saying, is there a significant difference? And in this case, yes, there is a significant difference. I'm saying that the people who took the 2-semester remediation class didn't do as well as this new class that has a co-requisite English class. Let's take a look now at a means question where sigma is unknown. And if you'll recall from 2 weeks ago when we did confidence intervals with 2 samples, we were very interested in whether or not the variances were equal or unequal. So in this case, we are not given any information about the variances. We're given their standard deviations, but we're going to assume that these variances are unequal, again, because they're from 2 very different firms. We can't assume that those variances are the same. So the t-score, and again, we're using t because it's a means question where sigma is unknown, just like last week or 2 weeks ago when we found the confidence interval and had to use the t distribution as opposed to the normal distribution. Just as we did before, we're going to find mean 1 minus mean 2 minus the hypothesized difference, which is typically 0. And then in this case, instead of sigma, we're just taking S1 squared divided by N1 plus S2 squared divided by N2. So that's all I've done here for my t-score formula. And then for left-tailed, again, I'm doing t-dist. And then the t-distribution actually is kind of cool because it actually has t-dist right, and it has t-dist two-tailed. So notice I've just utilized each of those, but they're all dependent on this df, which is the degrees of freedom. And I didn't fill this in ahead of time, so the degrees of freedom is found by comparing N1 and N2. So for this one, I'm going to write if N1 is less than oh, sorry, I just did that. Let me try again. Equals if parentheses N1 is less than N2, then I want to use, so value if true, I want to use N1 minus 1. And if it's not true, that means N2 must be the smaller one, so I'm going to take N2 minus 1. That is the degrees of freedom. So then I'm going to look at, again, I've already looked at left-tailed, right-tailed, two-tailed, so let's fill in our values. We're looking at two CPA firms in Chicago. Smith says its clients receive larger tax refunds than Jones and Company. So we're going to let Smith be the first sample, and the second sample is going to be Jones. So my null hypothesis is just going to be that those two means are equal to one another. My alternative hypothesis is going to be that Smith gets larger tax refunds. The mean for Smith is greater than the mean for Jones. And that's going to tell me that this is the value that I'm going to be looking for. So again, it's always important to know what it is that you're looking for. The mean for my first set, which is Smith's sample, is that there were 15 clients who had a tax refund of $942 with a standard deviation of 103, and again that was 15 clients. And then for Jones and Company, a random sample of 18 clients had a mean refund of $898, standard deviation of 95, and that was 18 clients. I'm assuming they are the same, so the hypothesized difference is 0, and alpha is 0.05. And then notice it's already calculated my degrees of freedom, which is 14, which is the smaller of 15 minus 1 and 18 minus 1. Again, my t-score is 942 minus 898 minus 0, and then I'm dividing it by the standard deviations, and it's 1.2656. Again, never a bad idea to look at your picture, so 1.26, 1.27, and I'm finding what's the area to the right of that, so it makes perfect sense that it would be smaller than 0.5, obviously, because 0 is here in the middle. So I get a right tail value of 0.1132. Remember, I'm always comparing p to alpha, so if p is less than alpha, I reject. If p is greater than alpha, I fail to reject. So what am I going to do here? Well, p is 0.1132 and alpha is 0.005. So p is greater than alpha, so I am going to fail to reject. So what does that mean? That means that there's not sufficient evidence to say that the alternative is true. The alternative says that Smith clients get a bigger tax refund. So I can say with 95% confidence that the sample that I've collected does not provide sufficient evidence to say that Smith clients get larger tax refunds than the Jones clients. Let's take a look at another question, and this one is, the concept isn't any more difficult than the one that we just did, but the formula sure is. This guy right here is a beast because it's so stinking easy to mess up your parentheses, to mess up how you enter this in. And so again, we're going to look at this question, and this is an equal variances question. So we're looking at a home improvement warehouse. They're saying, hey, come to our tiling workshop. You're going to spend less time than the people who don't come to our workshop in a tiling project. So we're going to assume that the null hypothesis is that the two groups will spend the same average time tiling. The alternative hypothesis is that the first group, the group that goes to the workshop, will spend less time tiling. So I'm going to be looking at a left-tailed test. So again, the t-score is really the hardest part because I have to correctly put all of this into Excel. So the really difficult part is making sure that all of your parentheses are correct, because I need the parentheses here to show Excel that this is one value and that entire value is being divided by everything here. So look at how many parentheses I'm using. I've got parenthesis and then the square root of parenthesis, parenthesis, parenthesis. It's kind of out of control, but I'm going to leave it up here so you can see exactly how I put it in. And my suggestion to you is, because this is what I do when I'm making my spreadsheets, is to do a question you already know the answer to, like this one that we're going to go through together, to make sure that you get the same answers that I do, and then you'll know that your spreadsheet is set up correctly. So again, the t-score is the hard part. From there, the left-tailed p-value is just t-dist of that value, and then of course the degrees of freedom, which for an equal variances question is the first n value plus the second n value minus 2. And the right-tailed again uses t-dist right. The t-dist two-tailed didn't work for me in this case, so I just went back to what I did before. If the t-score is less than 0, I need 2 of these. If it's greater than 0, I need 2 of these. So let's take a look. The first group of 10 customers, so each group has 10 customers, so I'm going to fill that in for N1 and N2. The first group is my group that went to the project workshop, and that group spent 14.1 hours completing their project with a standard deviation of 2.3 hours. The second group spent 15 hours with a standard deviation of 2.4 hours. I'm assuming that they're going to be equal. I'm using an alpha level of 0.01. Everything else has now been calculated for me. And what does this tell me? So again, I've used my little math nerdology to find that I should fail to reject. But you don't have to do that. You can just work it out. Remember, I'm looking for, is p less than alpha? Well, p for my left-tailed test is 0.20. Alpha is 0.01, so 0.2 is not less than 0.01, and so therefore I need to fail to reject. So what does that mean? That's my biggest thing, is do you know what you just found? I found that I need to fail to reject, and that means there's not enough evidence at the 0.01 level of significance to say that the people who complete the tiling workshops will take less time on average to complete their projects than those who do not attend the workshop. Let's take a look now at a paired question. So all of the examples that we've looked at so far were independent samples, and in this case I want to look at dependent samples. So what we're dealing with is sets of twins. And the first I didn't label very well, but the first column is weights of a twin that was raised in an urban environment, and in column B is the corresponding twin who is raised in a rural environment. And we're interested in the differences in their weights. So Dr. Chang has assumed that there's going to be a difference in the weights in an urban versus a rural setting. So again, it's always important, even though I don't ask you specifically for this as you're working through your questions. They will in Hawks, of course, but as you're working through your project, I won't make you write the hypotheses. But the null hypothesis is that the mean weights of the two groups are going to be equal, and I wrote that incorrectly. Remember, we're looking at the D, the mean of differences. We're expecting it to be 0. Then we're going to say, okay, what's the alternative? Well, we're looking at the a difference in the weight between the two groups. So we're just going to say that the difference is not 0. We're not going to say that the urban weight is greater or that the rural weight is greater. We're just saying there's a difference. So that is a two-tailed test. So this is the one I'm going to be looking at here, and we'll get to all of the formulas that I used. Again, I'm finding the t-score, and this one's actually a really easy formula because I'm not using this column of data, and I'm not using this column of data. I'm using this column that says, let's take the second value minus the first value. So I took B1 minus A1, B2 minus A2, and so on. The hypothesized difference was 0. That's this guy. The mean of differences is just the average of these values. The standard deviation is the standard deviation of these values. The number is the count of these values only. Degrees of freedom is just n minus 1, just like it was last week for our one sample tests. And then alpha is 0.01. So again, the t-score is really easy, especially after that last example we just did. The t-score is just the observed of what we have found, F2, which is the mean of the differences, minus what we expect the differences to be, which is usually 0, divided by the standard deviation divided by the square root of the sample size. Again, make sure you're using sample size and not degrees of freedom. The degrees of freedom will come into play here for t-dist right, or my two-tailed. So as you can see, I've already kind of filled everything in and included my conclusion cells here. What I should assume is that I should fail to reject the null. So even though there appears to be a little bit of a difference in weights, the difference was not large enough to be statistically significant. There's not sufficient evidence to say that the mean difference between the weights of male identical twins is not 0 for twins who are raised in different settings. So the evidence does not support Dr. Chang's claim that there is a significant difference based on where the twin was raised. Let's take a look at our last example, and this is a proportions question. Remember, proportion just gives us a part of a whole, which is a percentage between 0 and 1. And in this one, we're looking at the Surgeon General's call to action, and it was an initiative aimed at promoting walking and walkable communities, and the idea was that after this push or after this campaign, this community where the call to action was promoted would identify walking different than the rest of the nation. So identify those healthy habits at a different rate than the rest of the nation. So what this means to us is that the null hypothesis says that, again, we have two proportions. So we've got P1 is equal to P2, and we're going to let P1 be the nation, because we're going to compare the community to the nation. So the alternative hypothesis is that it was different than that of the nation. So the proportion of local adults who could correctly identify the Surgeon General's call to action was different. So that doesn't tell us a direction, it just says not equal to. So this is going to be a two-tailed test. Now keep in mind that this is the z-score formula, and again, we haven't seen this before, but we kind of have seen all the parts of it because a couple of weeks ago when we did confidence intervals, we were dealing with this whole standard error that we have on the bottom here. Just as a reminder, P bar is taking the number favorable plus the number favorable of the other sample and dividing by the total number in both samples together. And so that's the value that you're going to find. And then of course, because we're in a proportion, we're back to the normal distribution as opposed to the t-distribution. So I kind of like this question because it really makes you think a little bit. For the first part, remember, we're letting A, or 1, be the nation. So it says that in the nationwide survey of 4,114, so that's 4114, it gave me the proportion of 0.448. So typically I would have Excel calculate this for me, but now I'm going to have Excel calculate the number favorable. So remember that p hat is x over n, and so typically they give you x and n, and then you divide them to find p hat. So in this case they're giving me p hat. I need to find x, so I'm going to take p hat times n to get x. So that's what I'm going to put here, is p hat times n. And then for the second one, which is the local group, found that 65 out of 121 were able to correctly identify walking as the call to action. I'm assuming that those numbers will be the same. I'm using an alpha level of 0.05. And then again, what I'm looking at is a two-tailed test. It's two-tailed because I'm just wondering, is the percentage going to be different? So that means, because again we're always looking at is p, not p hat. I'm looking at the p value. If p is less than alpha, then we reject. So p for a two-tailed test is 0.0519 and alpha is 0.05. So those values are close, but p is still not less, so I have to fail to reject. So I have to say my interpretation is that the evidence does not sufficiently support the community leader's claim that the proportion of local adults who could identify walking as the U.S. Surgeon General's call to action was different than that of other adults nationwide.